So if we think about just this as a trig integral, so remember we did a section on trig integrals. So remember we wanted to isolate secant squareds, right? Because those are, what, the derivative of tangent? Well, we could do that, but then we don't really have a tangent. So this one can be done just straightforward with identities, but it's just a little tricky. So this doesn't seem to get us anywhere. We could change this into tangent squared by the identity with tangent squared, but then we just have one secant here. So it doesn't seem to be going anywhere without some kind of trick in terms of a trig, just a straight trig integral. But in class, we did cosecant cubed, and we talked about how this is a good one for using a table. So for the table, this is simply number 71 in the table. 71 is secant cubed u du, and it equals 1/2 secant u times tangent u plus 1/2 natural log secant u plus tangent u plus c. That's a plus there. Always, when you do antiderivative, natural log. So this is what you can find right in the back of your book. And on exams, like you'd have to have a chart of these or a selection of these to choose from if we were going to test about using tables. Okay, and so what's the only difference here? So what does our u need to be? U equals 9x, du equals 9 dx. And therefore dx is du over 9. Is that where the difficulty was? So then you have secant cubed u times, what's dx? Du over 9. Now we're ready to apply the table. So basically, what are you going to have? You're going to have this whole thing divided by 9, but then you have to plug that 9x back in for u. Yeah?
What does it mean when it tells you the domain doesn't match the answer? I got that.
You didn't use absolute values on natural log. We've done lots. You had to, what's that?
I got never put in the natural log before, and it's fine.
No, there's lots of Weber problems we've had where you had to use absolute value to get it right. And we've done that on web work, yeah.
I think it's because like when you take, I had the same thing. It's just because the derivative, you had to account for the derivative, like 9x. Like at the end.
So basically here, this right here is exactly what the table is, right? So that we can just write down secant cubed u du is that thing from the table. Ours is then also divided by 9, and then our u is 9x. Does it make sense? So let's see if I can do it. So I'm going to do 1/9 times parentheses. Here we go. So I'll factor out the one. Okay, so 1/2 times secant of what? 9x times tangent of 9x. I'm going to get it right on the first try, and then you guys are going to be really mad. Natural log, and then absolute value. Shift, backslash, secant, 9x. Did I miss something? Okay, plus tangent, 9x. And this plus c is already there. So does that match? So I can preview. Preview doesn't waste an attempt. Uh-oh. But it was just a preview. Okay. Yeah, because I did 1/9. I forgot that I had done 1/9 times the whole thing. Where is it? All right, so is that what we want? 1/2 secant 9x? I think this is right. Any questions? Green bar. Questions on this one? Using the table. Yes, sir.
On my homework, it was secant cubed is 6x. So does that mean we all have to pick slightly different?
Yeah, you guys get different problems. That's the beauty of web work. You don't get the same problem.
Okay.
Yeah. So you would have 1/6 and then 6x. Yeah. Okay, questions on this one? So what was the next one?
So you were able to use the rule just because you brought 1 9 out in front, correct?
What's that?
You were able to use the rule just because you moved the 1 9 in the front, correct?
I was able to use the rule because the rule is for secant cubed, and I have essentially secant cubed.
Yeah.
But then I have to do the substitution. I have to follow it through. I have to find out dx is not equal to du. If u equals 9x, then dx doesn't equal du. It equals du over 9. You have to figure that out. Okay, what else? Okay, so another table. So there's a whole section of forms of u squared plus a squared, the square root of u squared plus a squared. If you look in that whole section, and actually if you look at number 70, formula 71.
What number is this on the scoreboard? 8?
Yes. Is that the right? No, 20.
Yeah, so you just
25. 20. Did I just do 71?
Yeah,
25. Sorry. My notes are mixed up here. 25 says that the integral du over u squared plus a squared equals natural log of u plus integral of u squared plus a squared plus c. That's formula 25. We virtually have that. What is our value of a? 4. And the only other thing we have is this 2 out here. Okay, so, but u is going to be x. So du will be dx. I mean, basically you have u equals x. Du is going to be dx. You're going to have that 2, and then a is going to be 4. So we're ready to write down the answer. It's going to be 2 times natural log, absolute value of u, which is x, plus square root. Let's see, I'll just do it to the 1/2. So x squared plus a squared is going to be our 16 to the 1/2 power. And then parentheses, and then it says right here, note, use an uppercase C. It's telling you right there to use the C. Preview. So we had the 2 in our problem. There's the 2. Does it match the form? It does. Great. Questions on this one? Anybody have a question on that? Okay, and then the last one is the last one. So, what are we looking at here? So let's interpret, first of all. We have this integral from 6 to infinity, 1 over x to the 4/3 dx. What does it mean? So I think knowing what it means helps us to make sense of what's happening and what we're doing when we're actually doing the math. So this thing means, I think it's worth it to get a partner and take a minute and talk to each other. What does that thing mean? Go. Yeah.
This is totally unrelated, but I was looking at desktops.
So you know how to get to your you know how to get to your mission control, then you just go up here and you'll see a little plus will come up here. And then hit that and it'll do another one. It's called Omnidazzle. It's free. And you can do it on your thing, but it really helps to have this is a separate piece of hardware but the software is free, and you could do it. You could just do it with your finger, but it's kind of hard to write. So, but this then really enhances it. These are like if you got a deal on it, you get it for $30 or $40. That would be a deal. Like they're like retail's like 60 or 70 or something. Okay. So here's that function 1 over. So okay. Anyway, what did we say this was? This is volunteer. Somebody new we don't normally hear from. Who thinks they know what this thing means? Yes, sir.
It's a total change in a function whose rate is whenever x from 6 to
Nice. So it's the total change in some quantity or some function whose rate of change is 1 over x to the 4/3, and then as x changes from 6 to infinity. So here is that rate function, 1 over x to the 4/3. So before we do any math, what do we think? Does it, and we're going to start at 6. So let me zoom in this way. It doesn't like me. What's happening? There we go. There we go. Okay, so here's that function. There we go. So here is 6. And this is the rate, and we're talking about, oh, this doesn't work. Let's change desktops. Let's see. Okay, so this should work now. Thank you. Okay, so here's 6. And we're going to go from 6, that's x equals 6, to infinity. So looking at this rate function, thinking about accumulating at this rate starting from 6 to infinity, and asking, will it converge? Will it be a finite value, that total amount of the quantity, or will it diverge? Or maybe we should just ask, does it have a chance to converge? Does it have a chance to converge? Or can we say conclusively that it would diverge, meaning that quantity would get infinitely large? So, is there a chance? Yeah.
Yes, there is a chance.
Why?
Because the rate's decreasing
Uh-huh.
and it's always positive.
Okay. Right. So it's always positive, but it's decreasing, and it looks like it's approaching 0. And this indeed will get very, very close to 0. So as x gets very large, that rate will get very, very small. So the question is, will it get small enough, fast enough, for our total amount of our quantity to be a finite amount, or will it will get small, but it won't get small fast enough, and it's still the quantity could still blow up and be infinite. So kind of the jury is out with the situation. We've got the type of rate function that could give us a finite amount, but we have to do the math. Okay? So do the math, and hopefully that's so first of all, we can't plug infinity in, but we can take limits, right? So limit as a goes to infinity of 6 to a, and basically this is x to the minus 4/3, right? And we live and die for integrals like this now, right? X to the, oh no, yeah, you're right, negative 1/3, because we're going to add 1, and then we're going to have negative 3, and we're going to take that from 6 to a, and then after we plug in our 6 and our a, we're going to take the limit. So it's going to be the limit as a infinity of negative 3a, or I'll do 1 over a to the 1/3. That's what a to the minus 1/3 is going to be, plus 3 times 1 over 6 to the 1/3. Did you follow that step? I plugged in a, I plugged in 6, and I subtracted. Okay? So now, as a gets really, really big, what does that do? 1 over a to the 1/3. Yeah, that's going to, so that, yeah. As a gets really, really large, a to the 1/3 gets really, 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 really large, and then 1 over that would be 0. So that whole thing is 0. And so then this equals 3 over 6 to the 1/3, indicating that this indeed does give us a finite quantity. This is called convergent. So this is called a convergent improper integral. And then they said if it's convergent, you're supposed to put the value in.
Why do they call it improper?
So improper integrals means that something is running to infinity. There's something going on. So this, we're going to let that rate function run for infinity, and we're going to calculate the total change in the amount as we run out just infinitely. So that improper has to do with, it's involving something to do with going on forever. But proper integrals have a definite, proper integral either doesn't have bounds or has definite finite bounds. Okay, questions on this one? Okay, so let's continue. That's a good springboard for what I'm going to do next here. Here. Now we'll just work on this page. Yeah, okay. All right, so look at these two. So if these are rate functions, which rate function has a better chance of, if we were finding the amount of the quantity to positive infinity, which rate function would have a better chance of giving us a convergent or finite amount of the quantity? Purple or red? Red would have a better chance. I don't seem like tricky like that. Okay, now what do you think? What has a better chance? Purple. Okay, so the purple one has a chance to do it. Red does not. So the purple one is 10 over x squared. That's that rate function. And the red one is 1 over x. Okay, so 10 over x squared is a lot bigger when x is small. But then when x's get large, 10 over x squared is gonna shoot down way underneath this. So like at x equals 100, what is our rate of change? So at x equals 100, 10 over x squared equals, so it's going to be like 10 over 10,000 or 1 1,000th. And 1 over 100 is 1 100th. So we're not even close to getting to large numbers. X equals 100 in the scheme of things is very, very small. And already the rate function 10 over x squared it has a rate of change of 1 1,000th, whereas 1 over x is 1 100th. And so we actually kind of did these examples last time, and we saw that this form, 1 over x squared, or the integral of, I should say. Let's see here. So the integral of 1 over x squared, just say 1 to infinity. We did that example last time, we found that converged. And then we did an example of 1 over x, which also, that rate function does make it to 0. But we did the math, and we saw this diverged, meaning the total change in the quantity just kept getting bigger and bigger. Okay? And that's what we'll have here. So for that red graph, 1 over x, doesn't get to 0 fast enough for that quantity to level off. right? It just, that quantity will just keep increasing indefinitely, but 1 over x squared does. So the question is, where's the breaking point? So where between, say, 1 over x squared and 1 over x, what's the breaking point where we get convergence or not? Okay, so if we're looking at, say, 1 over x to the p, and we're going to say go from 1 to infinity. Say, for what value of p, or values of p, does the integral converge? We know it does when p equals 2. We know it doesn't when p equals 1. And how do you know? So prove it. So they're saying p greater than 1. So prove it. So let's do it. Ready? So we're going to do limit as a goes to infinity of 1 to a, 1 over x to the p, or I'll do x to the minus p dx. And that's going to be the limit as a goes to infinity of x to the negative p plus 1 over what? Negative p plus 1. That's just our power rule. That's all it is, power rule. So from 1 to a. Okay, so it's going to be a, so 1 over negative p plus 1, a, 1 over, let's see, what would that be? That would be 1 over a to the p minus 1, right? Put it in the denominator, and you take the opposite of the exponent. So I plugged in a, and I moved that thing in the denominator at the same time. Is it okay? Minus 1 over negative p plus 1. All we got to do is, for this one, just plug 1 into that, and that's just 1. Okay, make sure you understand that. I plugged in my a and my 1. I moved that thing into the denominator. Yes, sir?
Wait, just to make sure, it's 1 over minus p plus 1 times 1 over a power p.
Whoa, so start again. Where are you looking? This right here?
Yeah.
So I just pulled out this, 1 over negative p plus 1, and then I plugged a in for x, and then I moved it into the denominator. And when you move it to the denominator, you take the opposite of the exponent. Right? When you move a term to the denominator, it's the opposite of the exponent. Like x cubed, like x to the minus 3 is 1 over x cubed. So the opposite of this exponent is p minus 1.
No, I'm just wondering if it, like, between those two functions, 1 over minus p plus 1,
Uh-huh.
is it times?
Yeah, times.
Okay.
It's just because I just split this up into 2 terms.
I'll just write
1 over that times that. Yeah, 1 over that times that. Okay, so what we're asking is, for what values of p is this finite? Or, well, that only has to do with, so this is always finite. Okay, and this is always finite. Difficulty p equals 1. Okay, anyway, all right. So so it really comes down to this right here, right? Because as a gets really, really big, we're saying for what values of p will this behave, right? So if this doesn't behave, then it'll diverge, and if this behaves, then it won't. It will converge. Okay, so limit as a goes to infinity, we're just really focused in on that term right there, a over p minus 1. So in order for 1 over a to the something to converge as a goes to infinity, that something needs to be simply greater than 0. So 1 over a to the anything positive will get really small as a gets really big. So as long as this is a positive value, that thing will go to 0. So then we're saying p minus 1 has to be greater than 0, or p greater than 1, and that's what they said. And that fits what happened with us, right? So we had 10 over x squared. What was the value of p for that? The value of p is 2, which is greater than 1, and it converged. What's the value of p for this one? 1. And what happened? It diverged. We showed that last time. And then we had our Webwork example. We had y equals 1 over x to the 4/3. What's p? P is 4/3. 4/3 is greater than 1. We saw that when that Webwork example converged. So if you have an improper integral of this form, which is a very narrow form, by the way, this is not. We can come up with many more improper integrals. We'll do a couple different examples, but just this particular type, as long as p is greater than 1, you know that it will converge. We just proved it. And if p is less than 1, or between 0 and 1, it will not converge, including 1. All right, including 1. It's divergent. So this, like I said, this is a very narrow class of improper integrals. So it's all the ones we've done so far, but it's just a narrow family of improper integrals. So we need to look at other ones too. But they're common, so we make that general rule that if p is greater than 1, it converges. If it's not, it doesn't converge. Okay, so let's look at a couple more of these improper integrals. Questions on this derivation proof? Yeah, I mean, the whole premise of this, what I just did, was for what values of p does the integral converge? This form, this very narrow form, 1 over x to the p, which is a very small class of integrals. But it's a common problem. So it's a common, you see them commonly. Why? Because they're rate functions that go to 0, right? So 1 over x to the p, they're all rate functions that go to 0. Yeah. Did that answer it?
Yeah.
Okay. Cool. So let's look at a different one here. So here is 1. So let's just go ahead from 0. So we're going to talk about the integral from 0 to infinity of 2 over x plus 1 dx. And here is the graph of y equals 2x over x plus 1. Okay, so initial reactions. Definitely convergent, maybe convergent, definitely not convergent. Lots of different comments, heads nodding, heads shaking, maybe divergent. What do you think?
The acceleration keeps getting bigger and bigger.
Okay.
So it would never converge to 0, so the number would just keep getting bigger and bigger, so it would never actually reach.
What's that?
It would converge to 2.
Does it converge? Does this converge to 2?
I see like 2x over x.
So okay, so this function. Oh, sorry. This function, I will tell you, if you remember from your pre-cal, that's a rational function, and that it will approach, as x goes to infinity, will approach 2 over 1 or 2. So y will go to 2 as x approaches infinity. So, convergent or divergent? Oh, it's split 50-50. What function is this in this context? Yes, sir? Okay, right. What kind of function is this? 2x in this context, 2x over x plus 1 is what kind of function? Please know what kind of function 2x over x plus 1 is. Rate of change. Rate of change. Rate of change means how much the quantity increases per unit. So here we are at 9. How much is that quantity going to increase per unit when x gets to 9? Something close to 2, right? And then let me zoom out on the x-axis. So if you zoom out on the x-axis, basically you get to a point where it's indistinguishable from 2. Every single y value of this rate function is indistinguishable from 2. It gets so close to 2. So at x equals 180, how much does the quantity grow by per unit? 2. At x equals 181, how much does the quantity grow by per unit? 2. At x equals 1,000,000, how much does the quantity grow by per unit? Is this quantity going to converge? No, it's just going to, what's going to keep happening every unit of x? It's going to grow by 2. It's going to keep growing by 2, plus 2, plus 2, plus 2, plus 2, plus 2, plus 2 for every unit of x and on for infinity. So this is horribly divergent, right? It's not even close. So you got to know what you're looking at. This is the rate function. So yes, the rate function converges to 2, but the rate function means how much the quantity grows every unit. So it's going to grow by 2 every unit. And if it does that for infinity, you just keep adding 2 for infinity. Yeah?
So that's a position function, it converges to 2.
That function converges to 2. But in that context, it's a rate of change. You see? In the context of an integral, that is the rate of change.
So if it's an integral, it diverges. But if it's not an integral, it doesn't diverge.
Yeah, so yes. As a function, just as a function by itself, it approaches 2 as x approaches infinity.
So rate
But we're asking about this integral. And in this context of this integral, it's a rate of change. And so so the only chance that an integral has to converge is if the rate of change does what? Goes to 0. That's what we've been saying. It's got to get small fast enough so that you end up adding a negligible amount as x goes to infinity, not a finite amount, not some constant amount. You got to keep adding something that turns out to essentially be 0, and you keep adding 0. Therefore, you can get a convergent total amount of the quantity. All right, so I'll make sure you understand this. Does it make sense? Really important principle. Okay, so another one. So we don't have to do any math. Well, that conversation was definitely math. No algebra. No algebra needed. If we know what's going on, we just say divergent. Okay, another example. How about this one? So here's negative 3x e to the x, and this is going to be from negative infinity to, let's say, negative 1. Yes, sir?
If we have a question on a test like this, would sketching the graph be enough work to show that it's divergent?
Well, you have to know that function, like that last one, you could sketch the graph, but you have to then give some justification for why that function it's leveling off at 2, right? So you got to have the right sketch and the right reasoning for the sketch. Okay, so here's one. And this is another type of improper also. So we're gonna like start way out at negative infinity, and then we're gonna accumulate up to 1, negative 1, at this rate, negative 3x e to the x dx. Okay, so definitely divergent, maybe convergent, definitely convergent. Which do you think?
Can you like flip it and then flip the sign inside? Like flip the integral and then flip the sign and then actual rate?
This is very uncomfortable to you.
Yeah.
It's the same thing. It's just you're starting. Just imagine starting at virtually, you know, way out to the left, and then we're going to accumulate to -1. So try to think outside the box instead of making it like the boxes before. So does this have it? So the question is, does it have a chance to converge? Yes, because this, as long as this gets small enough, fast enough, then it could be adding a negligible amount so that the total amount of the quantity is finite. Okay, so the question is, how do we do that right there? So we need so there's another element. After we do this problem, we'll explore a whole other element to this. All these techniques that we've been doing is now just given any integral, do you know which technique to apply, or can you find out pretty fast? So here's an example of that. Do you recognize? Let's write down all our techniques. So we got undoing chain is first. Then we had undoing product. And then we had trig, identities. And then we had partial fractions. Is that next? And then we had use sub techniques and tables. Those, I think that, did I miss one? I think that was all that we worked on. So, which of those 5? And always ask if it's undoing chain first. Always look, is it undoing the chain rule? How could you change it so that it would be undoing the chain rule? E to the x squared. If it were e to the x squared, there's your derivative x of the internal function x squared. But we don't have that. We have x e to the x. And this is actually a very common form for the technique that you would use. What is it? Undoing product. Undoing product. This is perfect for undoing product. Okay, so let's review it. Here we go. So let me rewrite it. We're going to do the limit as a goes to infinity of, or we'll do a goes to minus infinity of a to -1, -3, x e to x. Okay, remember what we do. It's f and g prime. And so remember, we think maybe f will be the one that would kind of simplify if we took the derivative of it. And then g prime has to be something we can do the antiderivative of pretty easily. So f is, let's just throw the -3 in there, that's fine, -3x. F prime is -3. G prime, g. And so remember our form was fg equals integral fg prime and what was the point? Remember? So this is the product. We think of this as one of the 2 terms coming out of the product rule, whereas the other term would be easier to do the antiderivative of. So we're thinking that would be easier. So we want to do that one instead of this one. And so all we need is fg, and then we need integral gf prime, and it's equal to that. So that's our answer. So fg is -3x e to x. So answer equals that minus integral e to x f prime. And then this will have the same limits of integration as the one we had started with. Oh, no, yeah. And that will be evaluated. So we could just do that at the end. So after we get everything evaluated, then we're going to evaluate from a to everything from a to -1. So we got -3x e to the x plus very easy integral, 3 e to the x, right? That makes it plus. So then we're going to evaluate from this whole thing from a to -1, and then take the limit as a goes to -infinity. Okay, here we go. Almost done. Gonna find out if this does indeed converge or not. It has a chance. You're telling me there's a chance. Negative 3 times negative 1 times e to the negative 1 plus 3e to the minus 1 plus 3a e to the a minus 3e to the a. How did I do? Agree with that? Please tell me if I made a mistake. Negative 3 times negative 1 e to the minus 1 plus 3 e to the minus 1. Now we're going to minus the 2 when we plug the a in. So it would be plus 3a e to the a minus, I think I got it. So now we got to get these limits, right? So that will just, we got to figure out what these limits are. So let's do that over here. I'll do it in blue and blue. So how about this? Can I do 3a over e to the minus a? And then minus 3 over e to the minus a? So I'm just working on this right here. We're hoping it goes to 0. If it goes to 0, then it converges equaling that amount of change. So what do we get? We essentially get infinity over infinity. How do we handle a limit that is this indeterminate form, infinity over infinity? Remember? The Hapstalls Rule, right? So the Hapstalls Rule says that we can do... so what about this one? So as a goes to minus infinity, that thing is going to get really super big. That will definitely go to 0, first of all. So we got that. That one's gone. This one, so we have, it's the same as 3 over negative e to the negative a. And that definitely goes to 0. So we got this whole thing goes to 0. Conclusion? Convergent, and the value of the total change in the quantity will be 3 over e to the e plus 3 over e, or 6 over e. Okay, I kind of went fast through there. Please ask if I lost you on any of those steps. Yes, sir?
How'd you get from, you took 3a over e to the negative a, and then you went down to 3 over negative e to the negative a?
This here?
Yeah.
Yeah, so I just in order to make, so to get the Hapstalls Rule going here,
Okay.
I just, e to the a is the same as 1 over e to the minus a.
So yeah, and then, sorry, and then to the next step.
This step?
Yeah, that's.
The Hapstalls Rule. So I did derivative and derivative.
Gotcha.
So derivative of 3a is 3. Derivative of that is negative e to the minus a. So yeah, so I applied the Hapstalls Rule right here. We're going from that to that. What's that? Yep.
So Hapstalls Rule is why you moved the e to the a to the bottom.
Yeah, because I'm anticipating. I've seen this before, so I'm anticipating that I'm going to infinity over infinity if I do that, and then that I can use the Hapstalls Rule. Is that? If you don't do that, then you essentially get infinity times infinity, which is a similar indeterminate form, but you need it as infinity over infinity to use the Hapstalls Rule. Does that help? Okay. Other questions on this one? Okay, so conclusion about this rate function out here at negative infinity? Well, the integral converges, but conclusion about this rate function. It gets small, what? Fast enough. Fast enough, and that's the idea of an exponential function. When exponential functions are asymptotic to 0, they converge, okay? They get to 0 faster than 1 over x to the p, when p is greater than 1, okay? Okay, so that that does it for improper integrals. Any questions before we talk about the exam and do some review? Okay, so our exam is Monday night. Let's talk business about that. So your review, so if you go to Docs and Assignments, I posted the review materials last on Monday. So here in Wednesday's post is the review stuff. So review outline of topics, let's look at that. So this is just bullet points. This is what we did in the first week. Okay, and then as far as the written homework, what I will do is, rather than get it back to you, unless you want to come get it from me, rather than have it back to you in time for the test, I'm going to post solutions to those written homework. Okay, so I'll try to post those by Saturday, maybe, hopefully by Saturday. Okay, so all those, there's like 3 written homeworks that you had over this stuff. So I will post solutions to those written homework. And then after that first week, we did that stuff. Then we started our techniques of integration. I'm doing the chain rule, product rule, trig functions, partial fractions, substitution, tables, formulas. And so here's the thing that we kind of haven't practiced yet, but you have to know is recognizing. Recognizing which technique or combination of techniques should be applied. So when we did them all by type, right? So you were always anticipating, this is undoing the product rule, all these are undoing the product rule. But you need to be able to come to any of them jumbled up and figure out what to do, not only be able to know how to do it. All right, and then you're going to apply the techniques by hand, showing all your work, okay? And then the improper integrals, we just finished that up tonight, so you can read the bullet points there. So that's what the test covers, everything we've done up to now. And that is posted right there, review outline. So now the practice integral problems, we can start. Here's where you start getting some practice of figuring out which technique to use. And then there's some follow-up multiple choice questions. But I think for the rest of the time, I think we should do that. We should go through this list. You can do it in groups. And maybe just identify what technique and maybe just get started. You know, I mean, obviously we can't even do 5 of these in the rest of the time. But identify what technique you would use, and then just do like the first step, just the kind of that unlocking the lock, just to get you started, and then you can run out the algebra later. So as many of these as you can identify and just get started would be great, and then we can kind of, in the last 5 minutes, we can talk about the ones you have by request. Yes, sir?
I was just wondering
Your hand wasn't up. I didn't see your hand up. Was your hand up?
Yeah.
Okay.
Oh.
Sorry. Go ahead.
Oh, okay. I was just wondering if there's an answer key for these problems.
Yes. I'm going to post the answer key Sunday night,
Okay.
24 hours before the test.
All right.
So it's very good if you work on these without the answers. That's going to be the best way to study. If you start with the answers in front of you, this is not the way to study, because that's not what the test is like. Okay? All right? So seriously. So work on these before Sunday night, then I will post this answer key to this Sunday night. But don't start studying with the problems and the answers in front of you. This is it's a recipe for disaster. Okay? Your question?
And, are we gonna get a not cheat sheet, but one with all the formulas that we got from the first quiz, or was that gonna be memorized over the next?
So
Like a derivative secant or derivative secant squared, the formulas that are in the back as well.
yeah, well, okay, so if it's using tables, of course you're provided those. That's the whole point of those. So if you're going to do any table integrals, you'll have a bank of that. That's for sure. In terms of other formulas that I would give you, I have to take some time to think through that, so I'll post that to Blackboard by the weekend. Is that fair? Yeah, okay. So there may be some trig, but for instance, like the half angle formula for doing integral of sine squared and cosine squared. We see sine squared and cosine squared so much that you should just memorize that because you don't want to look that up every time you come to it. Yes, sir?
Will there be specifics on like how many questions the test will be?
Yeah, so I think it's like 15 or 20 multiple choice, and then I don't know, like 5 to 8 free response.
We have one.
So that's just a guess. 15 to 20 multiple choice. This is ballpark. 5 to 8 free response.
Is this all in one class period?
Yes, but there's no class in here afterwards, so you're welcome to stay longer. Yeah. Other questions about the exam? Yes, ma'am.
Any like conceptual? I know obviously the first part of the
Mhm.
test, all of the like what does this mean sets it up for
Yeah.
conceptual questions.
Yeah.
But are most of the actual interval questions going to be just like solving the problem? Or
Yes, and the other place for conceptual questions would be in the improper integrals, what we just did. So yeah, so the first week and the improper integrals would be the territory for do you understand concepts, and then but then it could do a mixture, right? So it could be a problem that is asking you that you understand things, but then also applying techniques to solve the integrals. Yeah. So yeah, the main concepts will be first week and improper. Other questions? Okay, so let me talk about before I let you loose working on these. So in terms of my office, so office hours would be tomorrow is my normal office hours from 3 to 4:30. Thursday 3 to 4:30. That's every week, every day, every Thursday. And then Friday. It will actually be available from 8 to 8:45. That's a review for another test. I'm not expecting a big crowd. And then also 2:45 to 4:45 P. So, and this is all ECA 209. So Thursday, tomorrow, 3 to 4:30. Friday, 8 to 8:45 in the morning, and 2:45 to 4:45 p.m. And then you can always email me questions, and I can do my best to. We can do our best to have a conversation over email about any questions that you have. I will post this as an announcement on Blackboard. Anything else we need to know about the exam? Monday nights. Okay, so once you get in groups of 2 or 3, just identify and get started to the point where you know you're home free, and then go on to another one and work on this initial stage of kind of unlocking the lock or solving the mystery to where it's just algebra left. Why do I touch it when it's fine? The only one on here I see that we couldn't, with the techniques that we learned that we couldn't do is 20. So don't worry about 20. That's the only one of these that I see that. What's that? To the 3 halves though? The reason I'm saying, yeah, because there's to the 1 half, but that's to the 3 halves. So maybe, but I don't know. I could look. Don't ask questions. Let it be. Let's see how many we can get through. Talking just starting. Requests. Number 9. Very important. So this pattern shows up a lot. Like it comes out in partial fractions sometimes, and you just have to. This was from like the first time, right from the beginning. We saw ones like this. Well, how do you handle this?
We split it.
You split it. That's what you do. You split it into x over x squared plus 1 and 1 over x squared plus 1.
So one's chain rule.
That's right. So this then is undoing the chain rule. X is the derivative of 2x. This is undoing chain. 1 over x squared plus 1. Arctangent. Arctangent. This shows up at the end of problems often. Like you'll do a technique and then you'll come to something like this, and then you got to recognize you got to split it up, and you have undoing the chain rule and arctangent. So you'll see that that's common. Another one. So yeah, 2. Okay, so what I see here is I've got cosine squared, and then I have up here I have sine. So I think to myself, what if I let u equal cosine x? Then du would be negative sine x dx. And lo and behold, look at that. That's right there, sine x dx. That's the opposite of du right there, negative du. So it becomes negative 2 over 1 plus u squared du. Do you recognize what that is? Arctangent. Arctangent. So it's a u sub and then arctangent. It's a u sub and then arctangent. Another request. 15. Okay, so I'm seeing secant to the 4th tangent squared, and I'm thinking, okay, the derivative of tangent is secant squared. 14 or 15? Go ahead.
Okay, 17.
17. Okay, so I've got all these cosines and all these sines. And so I think if I can just pull out one sine or one cosine as the derivative of the other, I can set this up to be undoing the chain rule. So do I want to pull out a sine or a cosine? A sine, because then I'll have all even powers left. So this is good. We never did one of these, but we talked about it. So if I do sine x, pull out a sine x, and I'm thinking that's going to be the derivative of cosine, and then I'll have sine to the 4th and cosine squared. So if I can get all of this in terms of cosine, if I can get all cosines in here, then I can do undoing the chain rule because then I have the derivative of cosine or sine. So I need to change this into cosine. So how do I do that? No, don't use half angle because that'll change the argument. So we want, yeah, so we want 1 sine squared is 1 minus, I don't have room here. Okay, so give me some room here. All right, so sine x times, was it sine to the 4th? Sine to the 4th is sine squared squared. And I had cosine to the
Square.
Yeah, square.
Okay, I'm a little nervous it's going to be ugly, but we can do it. All right, so then it's going to be sine x times, I want to get all cosines in here, right? I want to get all cosines so that we can undo the chain rule, and that'll be my derivative. So 1 minus cosine squared x squared. All right, it's a little ugly here because I got to multiply that out. But once I multiply that out, I've got all terms of cosine, and then I got the derivative of cosine right there. So here's what it'll be, sine x. So it'll be cosine squared times 1, cosine squared times negative 2 cosine squared, which would be negative 2 cosine to the 4th, and then cosine squared times cosine to the 4th, which is cosine to the 6th. And now I've got 3 undoing the chain rule, right? Sine x times that, undoing the chain rule. Sine x times 2 cosine to the 4th, undoing the chain rule. Sine x times cosine to the 6th, undoing the chain rule. So you just distribute the sign, and then you got 3 undoing the chain rules. Raising power on cosine. You're raising power on cosine. Okay, I'll stick around for another 5 or 10 minutes if you